All right, day 58, lesson 6.4, functions and formulas. This is the first of a couple of days that we're going to do working with formulas, and it fits in with the polynomial functions because a lot of formulas are polynomials. And actually, this is kind of a nice introduction to our last unit. Our last unit, chapter 7 in our textbook, has got all to do with measurement formulas. A lot of the formulas that we'll be taking today and tomorrow have to do with measurement, like area and volume and so on. So today's 3-minute review goal is review, because you've got lots of good skills with measurement and area and volume in that business, um, and skills working with them as well. To use formulas to solve problems involving functions. So there are two area formulas. This is the one that Mr. Coleman likes, and this is the one that we sort of teach in math class. As it turns out, they're the same, sort of, mostly the same, and we're going to show that. Show that the formulas give the same answer for the area of this circle. Okay, well, Mr. Coleman's formula is this one, d squared. D is 4.2. We can just sub her right in. Bash that into a calculator, and you get about 13.85 centimeters squared for area. But then you use good old pi r squared. Notice you got a little bit of work to do because this circle gives you the diameter. And so then we got pi times 2.1 squared, and you fire that into a calculator, and you get 13.85 as well. If you were to write down more decimals of accuracy, they might be off a little bit. Same as if you use 3.14 for pi, you'd be a little bit inaccurate. I'd like you to use your pi button for these formulas. If pi's in there, you should use your pi button. But up until a couple of decimal places, these formulas give you exactly the same thing. A circle has an area of 100. Find the radius. Use both formulas and show that they give the same answer. So here, the area is 100. So in this Mr. Coleman formula, the area is 100, and we want to find the radius actually. We'll solve this for the diameter and then just divide by 2 at the end. How does that sound? Sounds awesome. Okay. Well, to get d alone, first step, we're just using our good old equation solving skills. Divide both sides by that awful decimal. 100 divided by that is, bing bing, on the calculator, 127.4 about. And then take the square root. Now notice, even exponent from last day's class, we know there should be two solutions. You know, this should be positive and negative square root of that, which is around 11.28. But in this case, we know a diameter can't be negative. So we dismiss the negative value. Okay, that doesn't make sense for a diameter to be negative. So we stick with the positive one there only. Okay, no negatives allowed. Okay, well, what about the other formula? Well, I'm going to do something a little different here. I'm going to, because I know I want to solve for the radius, and the area is 100. I'm going to just rearrange this formula. But the first step is to get rid of the pi. Get rid of the pi, right? Divide by pi. And then I get a over pi. And I get r squared. I suppose I could have put 100 in there, but that's fine. And I'm going to take the square root of both sides. Then I get this new formula. And all I have to do then is substitute in 100 divided by pi into this equation. Maybe this equation is a little more difficult to to put in there, but I can just go the square root of 100 divided by pi, and that goes into the calculator, and I get the same thing, 5.64. Notice that's the diameter, so therefore the radius is half as much from the Mr. Coleman one, right? Radius is 11.28 divided by 2, and that's the same thing, centimeters. Okay? Good. Same formula. So explain or guess why Mr. Coleman prefers his version of the formula. Well, give it a guess, but here was my guesses. First of all, this one, maybe Mr. Coleman's calculator doesn't have a pi button, right? Right, that's possible. Maybe you just have those big clunky calculators and no fancy pi buttons. I actually asked him about this, and the reason is because the diameter is easy to measure. The diameter is easy to measure, where the radius is difficult. And then the formulas are about the same. This a decimal, maybe Mr. Coleman likes decimals better. But the main reason is because when you're measuring a circle, it's kind of hard to know where the center is, right? Well, when you're measuring the diameter, you just get a ruler, and the biggest value you can come up with on a ruler across the circle, well, that's the diameter. And you figure in a shop, that's probably a lot easier than us monkeying around with the formula. Well, what do you think? Which one do you prefer? Of course, I love the formula that's got a cool symbol like pi in it. Like, look at how awesome that symbol is. Wicked. Pi. All right, on to today's stuff. Essentially, today's stuff, we just learned most of it. Well, or reviewed most of it, because it'll be review of old stuff. But there are a few little things we want to talk about. So solve problems involving formulas drawn from real-world applications. We've been doing that 3-minute review, and then we'll do that later. Explain the role of constants and variables in a given formula, and we'll see what we're talking about here. So in this formula, there's constant and variable. So any number part that doesn't change, that right there, that's a constant. In that formula, it stayed the same. That's a constant. Even in that formula, that right there is a constant. It doesn't change. But the values that can change are called variables, right? And in fact, this one's the independent variable. It kind of takes the place of x. All the formula actions going on the right. This is the independent variable. It's a variable. We kind of think of it as the x, and so this one's the dependent. We also kind of, when we're talking about formulas, we also think the output, the answer. When we do a bunch of stuff and we get an answer, that's the area. That's kind of like the subject of the formula. That's what all this formula is about, is the area. It's the subject. And often what happens when we're dealing with functions and formulas is that we change the subject. Okay? So in questions such as 2, where we were solving for the independent variable, there are 2 approaches that we can take. And I actually did these 2 in this order too. We can substitute and solve, or we can rearrange then substitute. Each have their own strengths. Now, I'm going to go back and show you that I did actually that. There was the formula. I substitute, hang on, in number 2. There was the formula. I substituted in all the stuff I knew, and then I solved for the unknown, right? Basically, I made them all numbers, I substituted in, and then I solved for the last thing that was unknown. Where in this formula, what I did is I solved first. I changed the subject. The subject of this formula is the R. The R became the output into this new formula. Then I substituted the 100 in, and I solved. Well, these might feel the same to you, but they are different, and there's advantages and disadvantages of using either technique. You must know both, but you'll develop your own style. Generally, we substitute first. Substituting in is, getting numbers right away if the numbers are small and easy or the formula is difficult to work with. Okay? So that's kind of like the first way that we did. Generally, we rearrange then substitute. If we already had the rearranged formula, we don't need to rearrange. So, for instance, if we knew this formula straight off, well, we wouldn't have to rearrange. We just use the rearranged one. Now, that won't happen very often, but maybe once in a while. If we have to use the rearranged formula several times, so that would be the case if, say, we needed to find the radius of a bunch of different circles given their area. Oh, now the area is 400, what's the radius? No, now the area is 800, what's the radius? We'd be better off using the rearranged version rather than the original and having to go through the same steps over and over again. Okay, so what does this math look like in practice? We've got an ice cream cone. An ice cream cone has a volume of 200 milliliters and a diameter of 8 centimeters. What's the height of the cone? Okay, first of all, what's the formula for volume of a cone? Well, I can't remember. Well, this is one of the things that we're going to review in Chapter 7. But for now, I'm just going to give you your formulas. Okay, the volume of a cone is pi r cubed, pi r squared times h divided by 3. Okay, that's the volume of a cone. And in the question, we're given that the volume is 200 milliliters, which is weird, and the diameter is 8 centimeters. Well, if we need to, the radius is 4, right? Well, what's 200 milliliters? Well, 200 milliliters is the same as 200 centimeters cubed. So that's a 1-to-1 ratio. 1 milliliter equals 1 centimeter cubed. That's not very neat. I'm going to write that again. 1 milliliter equals 1 centimeter cubed. It's the way I always think of those little cubes that you played with in elementary school that had the little notches on them. That's 1 milliliter and 1 centimeter cubed if you got up the ruler. All right, well, what would it look like if we substitute and solve? Well, if we substituted and solve, I'm going to write down the formula first. Here's the formula. I know volume is 200. The diameter is 8, so the radius is 4. So I'm going to substitute in. And then I want to solve for h. Well, notice that all of this stuff here, all of this is numbers. And when a formula is difficult to deal with, maybe you want to get as many numbers as you can. So you could go in your calculator, pi times 4 squared divided by 3, and that ends up being, be careful on your calculator, all that stuff works out to 16.755. And notice I'm writing down a few decimal places. Well, and if you did that elsewhere, if it was a big long formula, then you'd have some numbers, and maybe you can deal with, instead of a difficult formula, some numbers, even though they're decimals. Now to solve for h, I divide by 16.755, and I get my answer, which is about 11.94 centimeters. So the cone is 11.94 centimeters tall. What is this? The solve then substitute? Well, solve then substitute is what we did in the second half of the 3-minute review. The volume was still 200, the radius was 4 still, but instead of finding the height and substituting straight in, I'm going to solve for that. So I think I got to get rid of everything but h here. Well, what am I going to do? Need to get rid of h. Well, I do the opposite of dividing by 3. The opposite of dividing by 3 is multiplying by 3. So I'm going to multiply by 3 on both sides. Maybe I'll make that a different color so it stands out. On the right side, that cancels, right? On the left side, I've got a new little left side to deal with. It's 3v equals pi r squared h. And again, I'm thinking about getting h alone. So that means I got to get rid of all of this crud here. Well, how do I get rid of the crud? It's the opposite operation. Well, what's the operation between crud and h? It's multiply. Opposite operation is divide. So I divide both sides by that, even out the scale. That cancels. And then I am left with 3v over pi r squared equals h. I've changed the subject. H is the subject now. And now notice that this is kind of like a brand new formula, right? And I could use this anytime I wanted to, if I chose. And now I can just substitute in. I've solved for h, now I substitute in. This has another advantage of not only can we use it over again for other problems, I can just reach for my calculator once. This is why I prefer to do this, because then I can reach for my calculator once. Make sure you don't mess up the bottom here. Put the bottom in brackets like this, and you should get about the same thing, right? Say, well, Mr. Estall, I prefer this one more. I prefer one over the other. Well, that's good. You should have your own style, but you need to be able to do both. And there's reasons why we'd want to do either of these, okay? So you need to practice both skills, and the homework sort of walks you through that, even though you might not like one of the methods. Example 2. In a warehouse, how are we doing for time? That's the last example. I'm going to pound through anyway. It feels like we're getting a little bit long. Yeah, we're getting a little bit long. Sorry about that. But this will be a quick one. In a warehouse, the amount of inventory, I, and skids, is given by that formula where I naught, I with little 0, I naught, or I 0, is the number of skids at the start of the month. D is the daily change, and T is the time and days since the start of the month. There's Ferd's model for his warehouse. Explain what Ferd's model tells you about the warehouse. Well, notice that that's in the spot of I 0. That's in the spot of D. So what story is this telling? Well, it means it started with the initial inventory is number of skids at the start. So we started, Ferd started with 132 skids. And the daily change is minus 11. You see that number, minus 11. But is losing, or shipping out or whatever, losing 11 skids a day. Per day or per week? What's the time here? Daily change. Daily change, no problem. Per day. Good. Now notice, just before we go on, B and C these are pretty quick questions here. We had a formula that had 1, 2, 3, 4 variables in it, almost like this one, right? That one had 4 variables in it too. 1, 2, 3. Pi is actually a constant, but this one had 1, 2, 3, 4 variables in it. But we set a couple of the variables to have a constant value. So then now it's a function. It's not a formula anymore. It's a function, right? Where I think of T as being the input and I, the number of skids after T days, is the output. This looks like a function now, not a formula. But I just wanted to mention that in positive. It's kind of like, or in passing rather, this variable became a constant, and that variable became a constant. It went from a 4-variable formula to a function. How long until Ferd's warehouse is out of inventory? Out of inventory, out of inventory, out of inventory. That means I equals 0. No inventory. So that means, which of my 2 techniques that I just used? Well, I substituted, right? I didn't solve for for t first, I substituted and solved. This was a sub and solve. And now I'm just going to get t alone, add 11t to both sides is what I did there, or just move that to that side, divide by 11, t equals 12. It will take 12 days. What type of model is this? Well, I equals 132 minus 11t. This kind of looked like, where if this is the output, 132 minus 11x. So if I thought of it this way, and I could rearrange it a little bit, I suppose, what kind of function is this? This is a linear function. Or I could say it's a degree 1 polynomial, right? Linear model. Y equals change of daily change times x plus 132 was the initial amount. Daily change, initial amount. I probably should have recognized that straight from the question. We've done so many of these in grade 11 and back in grade 9 that we should have recognized that. But now it kind of makes sense. Linear model. That's it for today's homework. Tomorrow is yet another day on formulas. We'll see some more fun with formulas tomorrow. So thanks for stopping by, MCT4C.